Welcome to the EarthWorks podcast, where our team will share the jargon of carbon from many of our turf friends from the past 30 years.
Hi, everybody. This is Joel Simmons for another EarthWorks podcast. Today, we're bringing the team back, and we're going to talk to some of the folks here at EarthWorks, and particularly, we have Mr. Lawrence Mayhew, who is our chemist, and joining me with Lawrence to have a in-depth geek out session, Mr. Jack Higgins, who you all know from the EarthWorks podcast and our senior agronomist here at EarthWorks. So Lawrence, welcome back. The podcast that we did with Lawrence back in the fall on humic acids was one of the most listened to podcasts. So you have been requested by not only our team, but a number of folks out in the audience world to bring you back so that we can spin everybody's head. And, you know, in full disclosure, we here at EarthWorks get the privilege and the honor of spending a good hour or two with Lawrence every Monday on a Zoom call. Ever since COVID started, we've been doing our geek out sessions with Lawrence, and I think Jack would agree with me. We get overwhelmed to the point where aspirin is needed just to calm the head down because we get so full of stuff. But we spent a lot of time, Lawrence, talking about humic acid, and I think that's an important subject. And again, so everybody understands, Lawrence is our chemist. He works with us in formulation. He's a consultant to our team. We lean on him extensively. Oftentimes when a client asks us something that we just don't know, our first call is to Lawrence. Because he knows. And so we get a good answer from Lawrence. Sometimes a lengthy answer, but that's very much what I was used to for the many years that I spent with Jerry Brunetti. And I would ask a simple question, and 3 hours later, I would finally get the answer or be finished with the conversation. Thank goodness, Lawrence, our conversations aren't quite as lengthy. And I think you suffered, or you enjoyed the same experience with Jerry that I have. But we spent a lot of time talking about humic acids, and Lawrence is generally recognized across the world as a premier humic acid specialist, was involved in establishing the Humic Products Trade Association, which we are proud members of. And we've been able to work with Lawrence closely in tweaking our products and building what we will contend is probably the strongest humic acid complex in our Foliars Plus products that are now powered by biocharge. So, gents, let's start spinning the head. One of the things that we wanted to talk about, Lawrence, and we can start off by talking about this concept, and we talk a lot about it for some reason on Mondays, about the essentiality of nutrients and this concept of the plant really taking up only 16 or 17 essential nutrients. Research you told me was done back in the 1939 era, but has been the staple of most fertility, quote unquote, fertility folks in the plant world for a long time. We know for a fact that when we test our products, we're running with, we have at least 60 as a minimum, it seems, minerals in these products. And there's what, 90 minerals? I mean, you would think that the plant is taking up the majority of this stuff in one fashion or another. So the concept of essentiality, or 16 minerals being the only thing the plant needs.
There's 75 minerals that are naturally found in plants and naturally occurring in soils. And they're all taken up by plants. What you referred to earlier was the Arnon and Stout 1939 paper that was published, and that's still the basis of fertilization in plant nutrition, almost globally, actually, which says there's 16 elements that plants need and everything else doesn't count. Well, there is a very large group of bioinorganic chemists who study quite the opposite, and they do recognize that there are a number of elements that are taken up by plants and microbes. The microbes get neglected in that Arnon and Stout thing. By the way, the Arnon and Stout was a soil, it wasn't even soil, it was a nutrient solution.
It was hydroponic.
It was a hydroponic.
Yeah, so they weren't even taking into account the soil piece of it.
No, a little tap water and throw some chemicals in, and this must be what plants need. Yeah. and it's took.
And this is what we've lived off across the world for the last 70 years.
Yeah, and national, international fertilizer laws are based on that still.
Yeah. I've had a number of quote unquote arguments with folks, when we've talked about all the minerals that we have in some of these products. Well, it doesn't really matter. There's only 16 that count anyway. Who cares? And how can you prove it? And blah, blah, blah. And that's been an ongoing battle that we've had, and it's getting very frustrating.
So you mentioned, Lawrence, that the microbes really got neglected in this. I mean, I guess in the hydroponic system, they weren't there. So they weren't.
Well, they're there, but they don't perform the same functions.
They're not doing exchanging.
There you go. Yeah.
With the medium, with the.
That's a big one. Yeah.
Mm-hmm. So let's talk a little bit about that. I mean, they're really there to exchange and deliver nutrient to the plant, and they're utilizing nutrient to do that. I think that's what you're saying.
Yeah, the nutrient requirement of a plant may be actually different than the nutrient requirement of a fungus, or the nutrient requirement of a bacteria, or a anything connected with the root system, the bacteria that are connected to the rhizosphere, which is where there are a lot of interactions going on between the microbes and the soil. And I always like to think that plants came along much later in the evolutionary cycle than bacteria. Bacteria were interacting and building soils, and along come this thing called plants, higher plants, that realized that these nutrients were of their benefit, and they discovered ways over millennia to supply nutrients to the microbes that are living in the soils. And the symbiotic relationship's been going on for billions of years. And we come along and we say, no, you only need 16 elements.
Right. That makes sense. Yes, that's perfectly sensible. Only need 16 of the 90 or whatever, 70 you said.
Which is, I can give you an example, like lanthanum, for example, which is one of the lanthanides, is taken up by plants, and it increases photosynthesis. It increases resistance to stress. A lot of benefits. The Chinese put on millions of tons of these lanthanides per year. They're very well known in other countries, but in the United States, they go, you don't need that. But now that the genomes are being described, we know that there are genetic commitments to bringing the lanthanides into plants. So if there's a genetic commitment by plants to encourage microbes to release things like, what the big one is? Iron. Iron is generally not available in soils. It's very unavailable.
Right.
And so these symbiotic relationships just grew out of years and years of coevolution.
What is lanthanite?
Pardon?
What is lanthanite?
Lanthanite?
Yeah.
Sounds like a mineral, but I'm not sure what that is.
Oh, the one you were just talking about. I might have made
sorry, lanthanum. Yeah.
Lanthanum, sorry.
Sorry. Yeah, number 59 on the periodic table.
Of course.
It is one of the elements, 13 elements that belong in a series of elements called the lanthanides, more commonly referred to as the rare earths. And the rare earth elements are more known to create images on TV screens like we're watching right now. And they have a lot of uses. They're very versatile, but they are critical to relieving stress and photosynthesis and interacting with a lot of microorganisms. And like I said, now the genome's been described for both of these. The genes required or have been described that are interactive, that are actually providing all these interactions. So
where would you find this? Where would you find this? I mean, how does a plant get this material?
The lanthanides?
Yeah.
How does it get it?
Yeah.
Primarily by interacting with calcium and exchanging with calcium. I can show you a slide too that brings that up.
Let's pull it up. And
I have a slide that we're kind of just led into it. So why don't I just
for those who are only listening, this is also broadcast on the YouTube channel. So we'll walk you through the slides when he's showing slides as best we can to help explain what what Lawrence is showing us. But if you really want to get into this, go pull us up on the YouTube channel or subscribe to the YouTube channel, and you can see all of the EarthWorks podcasts. But you know, like we were talking the other day, there's just so many of these things that are not being described. So what we're looking at is the periodical chart, a la Lawrence Mayhew.
Well, this is the complete periodic table as we know it right now. And on the header on the top of this, I have, are there really only 16 essential elements?
Exactly.
Okay, so I put little red squares around the elements that are considered essential by law.
So the 16 of them, let's list this real quick for people that aren't watching. Nitrogen,
gladly.
Phosphorus, potassium, sodium, magnesium, calcium, iron, manganese, boron, zinc, cobalt, molybdenum, chlorine, nickel, sodium, cobalt, and silicon are the, well, that's 17, but they're all listed in the 16 essentials.
And what about the other 59?
Exactly. What happens to them? Who cares? They don't need to be in the plant.
Okay, on this chart, I've indicated that some of these elements are radioactive and they really don't have any known benefits to plants. So I got them in little radioactive symbols. And here's what I do next with this chart. Any element in green on this chart, which is quite a few.
Which is almost all of them.
With the exception of the radioactive elements, primarily, with the exception of mercury and the exception of aluminum, and all the radioactive, and the exception of helium, neon, argon, krypton, xenon, because those are called inerts. They don't react with anything unless they're under high temperature and pressure. But they don't react with things in the systems that we deal with under natural systems, physiological conditions. Otherwise, all of these are taken up by plants. They've been detected in plants. You can run this analysis so easily nowadays. You send a plant root or a plant leaf, plant tissue off to a lab, tell them to grind it up and dissolve it with something and run ICP-MS analysis, and you'll get almost all of these in a plant. Some plants have more than others, some lack some, but overall they are detectable.
And this would be true even of a simple, botanically simple plant like a grass plant?
Yes, you'll probably find most of these in the plant. You certainly find all of these in natural soil systems.
Well, let me ask you this, Lawrence. Would you find all of these in a grass plant that's growing primarily in a sand medium?
No, that's where everything changes.
Yeah.
Sand is a real challenge, and I've been working with you guys now for a year or two.
And we've confused you because of it, but it's all good.
Well, here's what I think. I think in order to make a product work in a golf course sand situation, what grows in a desert, for example? So in order to get something to grow on your sandy conditions, I think you have to come as close as you possibly can to mimicking natural soils. That would be my recommendation. Okay, so I look at soils, and soils have all these things I have up on the screen now, about 75 elements is how it turns out. I know there's a product out there that brags 90, but 75 is the answer.
Which we happen to use, by the way, I believe. You're talking about the seawater extract.
Yeah, there is a seawater extract that uses the word 90 in their branding, but I analyzed it and only had 37 elements in it, and I called the guy up and
Oops.
He didn't like that phone call. But I am a researcher and I'm always looking for materials.
That's why we have you around.
Okay, so I'm going to click on this again and eliminate all the elements that are radioactive or known to be problem elements. I really should block out aluminum. I struggle with aluminum. There's nothing about aluminum that we know that is beneficial to plants. And as soon as aluminum becomes available, like under acid conditions, what do you got? You got a problem, right?
You got a dead plant.
Yeah. Aluminum is toxic to every living thing under the sun.
Now, having said that, Lawrence, I'll qualify one thing. We get a lot of calls because a lot of guys will look at their soil test and they'll see a fairly elevated aluminum level and they get concerned. And usually the response is there is really no concern to mobilizing aluminum until the pH hits what? Very low, right?
As soon as it starts getting under 7, it starts popping up. Yeah, it becomes
But it's got to be fairly acidic for aluminum to become available
acidic.
enough to become problematic.
Exactly.
And that level would, my understanding is it's in the 4s or even in the 3s. Is that fair?
Oh yeah.
Okay, so I mean,
Yeah.
unless your soil test pH is so low, so acidic, aluminum is not a concern to anybody on any soil test. So don't be too concerned. You know, I think the aluminum is natural to a lot of soils, and a lot of superintendents, a lot of clients of ours will ask that question. You know, I've got this outrageously high aluminum. We've seen some in the, you know, in 1,000+ range on a couple samples, and it really throws a red flag to superintendents. And as long as that pH is in the 3s, it's never going to be a problem.
Yeah, the aluminum that's extracted by a laboratory all depends upon the extractant that they're using.
Right.
That is the determining factor, not whether or not aluminum is an issue under your conditions. It's just that there's so many laboratory methods that'll give you different answers for aluminum and everything else as far as that goes. Okay, the reason why I put this up here is if you can see this visually, is to impress upon anybody who sees it that there's an awful lot of elements that are taken up by plants. Now, whether we understand why they're taken up is another thing, but it does lead to a lot of questions. I don't think they can be ignored. Let's put it that way. And as a product developer, I had a client a couple of years ago whose target became, I want all 75 elements that are naturally occurring in soils in my product, and we hit it. And you don't do that overnight. You got to try a lot of things, and you got to throw a lot of things into that blend, into that mixture to hit 75 elements in a product. But we did it.
And
okay.
We're pretty close to that on most of our liquids, right? I mean, between the analyses that we've recently run, we're pretty darn close to those numbers, if not really at that point, with the diversity that some of the products that you and I have built together on the last number of years.
Well, compared to a conventional linear approach, you're way ahead of the game.
Yeah,
way ahead.
We'll talk about that, but let's keep moving down this road here.
I just clicked on this to bring up this statement. Elements from top to bottom. In other words, look at magnesium and calcium, top to bottom, stacked on top of each other.
Mm-hmm.
They substitute for each other in nature, in natural reactions. Mm-hmm. And the substitution is done for two reasons. One, to modulate enzymatic activity, which happens all the time, or in the absence of the one above it or below it, the one will take the place of the other in any biological system. So let's say, here's a good example here, potassium. If potassium is deficient, then rubidium, the next one down, just below it on the periodic table, will substitute for potassium. That's been known since 1840. So, all right, this is a very, very common occurrence. It's a hard thing for most people to grasp. Or, I just said this, or it's a deficiency of the element. So one of two reasons. It's either going to be moderating the activity of the element that is substituting for. Now, this is all about enzymes. And
yeah, that one's a little strange. I mean, the first one that you start with, it modulates the enzymatic activity of the substituted element.
Yes.
I guess it's a little bit easier to think that it's to remedy the deficiency of the element, so it could substitute for that reason. But to modulate the enzymatic activity, what is that about?
In other words, enzymes just don't go. Enzymes are depending on what's going on around them.
Right, nothing exists in a vacuum. You're saying it's not just binary on and off. There's reasons.
It's like the accelerator on a car. You just don't get in and go boo. You have to rev up. You have to slow down. You have to stop. You have to do things. You have to adapt. And plants and microbes do the same thing with substitution with elements.
Okay, so let's talk about enzymatic activity to start with. I think what we're really talking about is the release of enzymes into the rhizosphere, whether it's from the plant or from the microbe, that to do a function. Enzymes do functions, right?
Yes.
Yeah. So I mean, I guess I'm trying to boil down, what is the enzymatic activity that we're talking about?
Wow, any enzymatic activity. There's thousands. There's endless, countless numbers of enzymes. They all have a duty, but a lot of them overlap with each other. What can we pick on? I'll give you an example here. How's that? Okay, so what I wanted to mention before I get off of this slide is that we have a lot of trace and ultra-trace elements that do the same thing, and they're like a microchip inserted when they're required. So that's kind of the analogy that I think works pretty good. These are like little bio-inorganic chips that are being inserted when they're needed and removed when they're needed. So there's always these interchanges going on. Now this is way beyond basic essentiality. I mean, this is a biological function that's occurring constantly and at the speed of light. Okay, so
and both in the plant and in the supporting biology of the plant.
Any living organism does this. Even we do it.
Right.
Okay.
Right.
Let me put up some common substitutions, not exotic ones, but real common. Okay. When you see an element on a periodic table like sodium and potassium stacked on top of each other, okay, what happens when you have too much sodium in a soil? What's one of the things you detect right away in regards to potassium?
You don't get the potassium uptake.
Why? Because the sodium substitutes for the potassium. So what do? You know, we put on too much sodium. So we got a problem. Now, on this graphic that I have up on the screen, rubidium is immediately below potassium. Rubidium will substitute for potassium. And below rubidium is cesium. Cesium will substitute for rubidium and potassium and sodium. And this is all on the periodic table. That's that guy that put it together many years ago.
There was rhyme and reason to why this was put together.
We talk
a lot about this to superintendents when we're talking about sodium issues, is that by keeping the potassium levels up, it can actually keep sodium from flushing into the plant. Is that a fair statement?
That's a great example of how.
And that's what you're seeing when you look at it on a periodical chart. They're stacked on top of each other. That's the definition right there.
Yeah.
So when we look at a soil test, one of the first things we look at is sodium levels, and we can identify sodium-induced wilt problems, big problems for a golf course superintendent or a sports turf manager. If we see the sodium level below the potassium level, we know we've got to get back in there aggressively with potassium and try to remove the sodium. But I've never seen it in this chart like you've laid it out here. That's fascinating to me. Of course, I didn't do very well in high school chemistry either. So there's
that's too bad. You would already know this.
Probably would have liked it if I'd known what I know now.
Okay, so what we have here, what I'm showing you on this graphic with these different elements stacked on top of each other in periodic table is really the basis of a flush product. Right. That's it right there. Okay, so that's essentially what you're looking at. In other words, somebody figured out you could take calcium, for example, and combat sodium problems. Yeah. Okay, that's the reason why. There's chemistry behind that. Now, take this one step further. Strontium substitutes for calcium, especially under stress conditions. So if a plant is under stress, the enzymes that are involved in utilizing calcium really get the message somehow that we have to modulate this calcium. It's modulated with strontium. Can you imagine guaranteeing strontium on a label? But yet this is occurring naturally in soil systems, plants, microbes, etc. Okay, I'm going to take it to a different level then. Take you somewhere where you've probably heard about this before. Silver. Silver is notorious for being an antibiotic, right?
Right.
Okay, so is copper. And they sit right on top of each other on the periodic table. So the chemistry is there, the logic is there, the practical common sense is there. I mean, these two can pretty well do the same thing. What happens when you add gold to these two? You now have a wedding ring, you now have jewelry. They're so compatible. They're so compatible with each other that they alloy with each other. We call it alloys in metallurgy. So you combine those two and you got 18 karat gold. If they were incompatible chemically, they would never mix. And
the same thing's happening biologically, you're saying. In biology, it's happening.
Yeah. You can find gold, you can find silver in extremely small quantities in plants, in their roots.
Wow.
It's because the chemistry says they ought to do this. It's predictable. Okay. Now, in 1884, this guy by the name of Sidney Ringer, who they ended up naming a nutrient solution after him, Ringer solution, discovered with a frog leg that potassium was the primary ion that was interchanging in muscles to make the frog leg move. He also found out, and I don't know how this knowledge got lost, that rubidium and cesium substituted for potassium in these frog leg reactions. So they've known about these interactions for an extremely long time.
And
if you're not watching this on YouTube, you're actually missing quite a wonderful little diagram here of the frog leg going up and down.
So do rubidium and cesium, are they in the same column on the periodic table as potassium and sodium? Did I miss that? All right.
Nope, the column is, starting at the bottom of the column is cesium, the next one is rubidium, the next one up is potassium.
Okay,
yeah.
Exactly.
On the periodic table.
Okay, interesting. There was just so that we can check back to high school, I remember them teaching us how they stack these together. And I know valence was a part of it. And I thought there was then a weight, right? Atomic weight or something like that.
Yeah. When we were talking about calcium substituting for sodium, one of the main reasons for that is because calcium has a double positive charge on it, whereas the sodium has a single positive charge, and that charge can overwhelm the single charged sodium. So there's a good example of what you're addressing. And there is a difference in molecular size, and there is size matters, and there is a difference in atomic radius. Molecular weight usually doesn't get involved in these charged reactions, which kind of leads us into redox reactions.
Okay, that was something that was on the list to discuss today.
Well, not everything is a redox reaction.
Explain the concept of redox reaction so people understand what we're talking about.
That's short. That's an abbreviation for reduction oxidation reactions, which simply say that if two things come together, one of them is going to be oxidized and the other one's going to be reduced. And these are just mathematical calculations of whether they gained or whether they lost charge, and when they did this. So it's an exchange of charges. So these charge transfers do occur to many things in nature, but not all things. And I could only come up with this one chart because there's an awful, oh, by the way, we got to put this in the context of physiology, not in the context of what goes on in a test tube. You know, it's a totally different world when we're talking about physiology. Okay, so
that's back to the 1939 study, hydroponics versus soil. You know, it's not happening in a vacuum. This is exchanging between living things,
and it's extremely dynamic. These living environments that were even the ones that I talked about earlier, these sand environments, ultimately become an extremely dynamic biological, chemical, physical environment.
They don't stay sterile for long once the grass plant germinates.
Once there's a plant,
and a biological system starts to develop around in that rhizosphere. So we all know that on our side.
Redox reactions, which is kind of interesting. It's called oxidizing reduction reactions, what they call them redox, which is reduction oxidizing, are based on the Brønsted classic definition of an acid and a base. However, in living systems, that's not necessarily the case what's going on. There's these metals interacting with enzymes primarily, and this interaction may be a sharing of electrons. So that means they're not Brønsted acids and bases, they're Lewis acid and bases in living systems. So what I did on this chart was I'm going to put a little red arrow next to every element on this chart. There's not many, there's only 16 or 18 here, of what we know are non-redox reactions within living systems. Magnesium is right on the top.
Magnesium is the first one. Okay.
Yeah, it's a non-redox element in living systems. That's why I got up here that
biological functions.
So that means it's a sharing.
A sharing, exactly. Lewis acids are sharing electrons. They're not They're not transferring it to one over here and totally losing them and changing their oxidation or their reduced state, redox.
Okay.
Notice that I didn't click sodium or potassium. They are
Right.
redox.
Or calcium.
Or calcium. They are redox. Chromium, you might wonder why I got chromium on there. Well, in the scientific literature, chromium is extremely critical to nitrogen fixation, and it's
Wow.
extremely critical to people who want to avoid using insulin to stay alive. So that's why it's on the chart. It is a critical biological element and thoroughly studied. Can't put it on a label. Molybdenum is non-redox. Tungsten, again, tungsten is very critical to enzymatic systems that are involved in nitrogen fixation and transfer of nitrogen through plants and microbes. Manganese is a really cool one. It goes through a process called dismutase, which is so cool and so hard to explain, but it's not a redox reaction. Manganese can actually change reduction in oxidative states with itself and through no exchange whatsoever create two different manganeses, starting out with one that has a certain redox potential and end up with two others that have totally different redox potentials. It's not a redox reaction. Absolutely fascinating. I skipped iron because it's
You
a
did.
redox. Yep. Cobalt is non-redox. Nickel, again, very critical to biological systems, and at least that one's been approved. I skipped copper, and the last one on this list is zinc as a non-redox. So I've been hearing so much about redox in the Gulf world that I thought I should bring this up.
Well, let's talk about that so that we don't lose everybody from high school chemistry days. But we keep talking about this idea of ROS. And correct me if I say this, reactive oxidative species. There you go. See, I knew you'd have a slide for this. You always have a slide. Explain.
I'm reading your mind.
We talk a lot about ROS, and
Yeah.
let's get into this a little bit, because this definitely affects everybody that's listening to this podcast, and superintendents and turf managers, landscapers, anybody dealing with plant material. Let's first define what ROS is, and then let's get into it in some detail, and then talk about how we're going to be able to manage that. But what is ROS?
I hear detail. I heard the word detail.
Well,
Cool.
yes, of course.
So
Within reason, let's have some detail. Yes.
I mean, let me tell you what they're not. They're not redox reactions. They are not.
Okay, and
The
tell,
ROS.
tell us why that was important to determine what nutrients did not go through that redox reaction, and tie that into this if you could.
Well, we've all been trained like everything is a redox reaction. I mean, that's the way my training was all through high school and college. And you can still pick up books that make it sound like every reaction on the face of the earth is a redox reaction. Oh my gosh, it's some of it.
Right, that it's a give and a take, and a give and a take, and it's always like that. You're right. The big
reason for mentioning it is that plants do not utilize highly soluble nutrients. They have devised ways to access the nutrients, and there's very, very little soluble nutrients in the natural soil system. There's hardly any. Like the number of pounds of soluble phosphorus per acre is 0.004 pounds per acre is in soil solution.
In a natural occurring soil environment.
Yeah. Or 21 days after you apply a highly soluble solution of phosphorus.
Right. Are we going to get into the line that plants don't drink, they eat?
They exchange.
They exchange, right?
Yeah. They're not just sucking up solution.
All right, so but let's go back. Let's get a definition down so that we all understand what ROS is. The center. We're looking at a slide here for those of you that are watching.
ROS is the plant version of human inflammation.
There you go.
Really
I love that analogy. I think that analogy is really important, because I think most of us understand what inflammation feels like. You get your hands swollen up. We even see it in plant material. I have a lot of turf managers come to me. My plants are puffy. You know, it's an inflammation. It's brought in too much salt, too much water, a lot of reactions going on. But inflammation is wonderful, because we all kind of know what that feels like, that, you know, have been living as long as some of us have.
The graphic that I have up on the screen right now is just a way of showing you that there's an awful lot of stresses that trigger ROS, the reactive oxygen species. Even high light intensity, which that has to happen on a golf course.
Oh,
And
yeah.
high temperatures. So high light intensity and high temperatures will trigger ROS.
Some of the
Yeah.
others listed here: drought, water deficient conditions, air
The big one,
soil salinity, of
that's
course, very big one.
huge.
Heavy metals, air pollutants.
Excess chloride ions,
Mm-hmm.
that's a big one.
Mm-hmm. And we
Yeah.
see a lot of that.
Now, I was told I wasn't supposed to talk about pesticides, but oh, by the way, they do this too.
Yeah, and a lot of things that we, that we have to do naturally in the business of turf will create some of these oxidative stresses, and
Well, walking on it.
yeah, physical. I mean, mowing the
About mowing.
grass. I mean, walking on it, having 200 people, 200 golfers a day on your golf greens are going to create a pretty strong ROS reaction, an oxidative stress reaction. And again, let's get a definition that is common sense on ROS. I mean, to me, what it is, it's this it's the same phenomenon in the human body where we've got these free radicals running around, and there's the way you described it to us has been an imbalance, but oxidation, reduction, and your picture here that most folks can't see is a lot of O2s and H2Os and OHs floating around. In a very practical term, I mean, in very, very basic terminology for everybody to truly understand, what is ROS?
ROS is when regular, plain old, everyday oxygen takes on a charge, an extra charge. It's energized.
Intracellularly?
The molecularly.
Even better.
And guess what? Nobody knows why. We only know that plants don't react well to stress.
Mm-hmm.
And what we do know is that, and I'll go into details here, we do know that the antioxidation processes, including antioxidants, including processes that are antioxidant, have to be balanced with ROS in order for the plants to survive that stress. We know that has to happen. Now, the part that I was really impressed with when I started doing some research on ROS was the sheer numbers. We only hear about a few of them out here, but I got singlet oxygen up on the screen right now. I don't know if you've ever heard of it before, but it's a common reaction by plants and humans, by the way, where oxygen totally changes its molecular structure and it becomes energized. And it's written down on the screen here with a little 1 in front of the O, and then the typical O2 that we're used to seeing. But it's not O2 anymore. It's been charged by some process that's not really fully understood. I got up on the screen now, the superoxide radical, which is an O2. It's oxygen, oxygen and oxygen combined with itself is O2. That's what we're breathing right now. We're breathing O2. But on this screen here, I get a little dot and a little dash next to it. That means it's picked up an electron and it's now negatively charged. Now it's a reactive oxygen species. It's not oxygen anymore. It's very, very reactive. And it's drawn like fluid acid drawing is the one I just threw up here. But I don't want to talk about that.
I don't want to interrupt the flow, but I believe that superoxide is what came up when I was learning about the rhizophagy cycle.
Yes.
That was part of the plant extracting nutrient from the microbe that had entered the plant.
Yes.
Okay.
Yes.
We can talk about that later.
We really need to talk about the rhizophagy because the rhizophagy cycle utilizes these reactive oxygen species. But at the same time, because it's utilizing them, it's reducing them also. It's using them up.
Aha.
So it's part of the way plants control this reactive oxygen species problem.
You showed on the last slide, it's really a balance. So when there is ROS in the plant, it needs to utilize it, needs to use them up, like you said. So
Yes.
It does things to use them up.
Mm-hmm.
Okay.
Whatever works.
Right.
A lot of things work, by the way. Hydrogen peroxide is on here. I think everybody probably recognizes H2O2. It's a very charged form of oxygen, very reactive. You put it on a cut or a scratch and you can see the oxygen bubbling out of the hydrogen peroxide. It's used as a medicinal. It's a topical. Everybody should be familiar with that.
That's been my go-to anytime I get a cut since I was a kid.
There you go. That highly reactive oxygen kills germs, right? Yeah. It's an antibiotic. It's an antibiotic. Well, you don't want to put an antibiotic in a plant or a microbe because it'll damage them. Okay, then there's a lot of them I'm not going to really go into, but I'm just every time I click, there's a new one that comes up, and I know what these mean, but what I'm really impressed with is that the variety of these things. I just thought there was 3 or 4 out there. Okay, how about this one, Hypobromus Acid? Plants can make that? It's like, wow, where does the bromine come from? Now, what really surprised me on this list were carbonates. The CO3 can take on an extra electron and become negatively charged. And now it's a reactive oxygen species, but it's one of many reactive oxygen species. Kind of interesting. Peroxide, alkyl, then I got hypergonal, about ozone. Ozone can become a reactive oxygen species, as if it weren't reactive enough already. That O3, that ozone molecule can take on an extra electron and now become a reactive oxygen species. It happens within plants.
I'm thinking about the stress that bicarbonates put on the golf courses and the fields that we work with, and how this carbonate with the extra negative charge is on the list of ROS of reactive oxygen species. I wonder if that ties together.
Probably.
Yeah, most likely, right?
Very likely, yeah. Now, one thing that's really impressive is how long these things last in a plant. Well, lightning strikes are about 0.008 of a second, 8 thousandths of a second.
But who's counting?
Okay. These things are like 10 times faster than that. They're 10 times faster than a lightning strike. So for the very, very short time that they're in existence, they do a lot of damage. So they got to be controlled. They have to be controlled. They must be in balance somehow because we got so many of them. I've got a picture now of a leaf up on the screen, just sort of graphically demonstrating how many are out there and how common they are and in a plant.
So now, you're looking at 15 or 15 or 16 different potential reactions going on that are going to cause this reaction, this oxidation reaction. So where you're going next now is we're going to talk about how do we affect this? How do we keep a balance within this process that is constantly happening? So these things are always being presented to anybody managing any plant material. I don't care if it's a blade of bent grass or poa or a petunia or a blueberry bush. All plant material are getting attacked on a regular basis or finding themselves in a situation where these oxidative species are imbalanced and causing some very serious stress factors. What would it look like if the plant was severely, for lack of a better word, attacked by these oxidative species? What would we see in the field on a plant material? What would the physical response be?
Apoptosis.
What would we see, though? What would we be looking at? Discolorization, dead plants?
Rattle, yeah. Brown leaves.
Okay.
Dead.
So things are just dying. I mean, it literally is just another reason why, an explanation is to, why is the plant dying or why is it going stressful? And in grass, I could see it happening on, various blades across the field. But move on to your next plant. So the next thing you're going to talk about here is how do we resolve this problem? And you've got up here a list of amino acids.
Yeah. I got glutamate right in smack dab in the center of this thing because it's responsible for generating other amino acids, even if it's applied exogenously, which is what we do. We apply it to a plant, either in the root system or the leaf system. And glutamate seems to be like the key of all amino acids. There's a lot of amino acids. I don't even know how many there are. There's 22 of them are very, very critical and very well studied. But the glutamate in this chart that I have up here is in the center because it does so many things. one of the things it does is it leads to another form of gluten of itself, another chemical form called glutamine. And glutamine is just another chemical form of glutamic acid and glutamates. So it's a very, very versatile amino acid. It can actually generate all these amino acids that I have up on the screen. I'll just mention a few. But what's really stunning about applying amino acids exogenously is that it increases chlorophyll. Chlorophyll is one of the best ways to combat ROS. In addition to everything else we know about chlorophyll, that's a huge, huge benefit right there.
Allowing the plant to produce chlorophyll, providing the materials, the minerals, the environment by which chlorophyll can easily run its course.
Chlorophyll is needed to convert sun energy into all the energies that are life-giving.
Exactly. We all know chlorophyll because that's what gives us our color green.
Yeah, yeah.
Well, so when we started this conversation, Lawrence, and again, I don't want to get too far down the chemistry 101 table, but we started this process talking with you as a team. We had decided to go ahead and do a amino acid assay of what we now call our biocharge base, which is the base of all of our liquid products, as a starting point for us here at EarthWorks. And we were quite amazed that this came back with such a diversity of amino acids. And the one thing, I mean, I think, Jack, you'll agree with me, when we first got this back and we were talking to Lawrence, you could see his excitement. One of the things that you were most excited about was all the glutamates, and you had highlighted them, and we're like, great, what does that mean? But, you were all excited about this. So we ended up with over 25 amino acids, but we had a very strong base, a very large percentage of those amino acids, which in this base of our Foliars Plus product line was the glutamates. And these are all there to grab and balance some of the reactive oxidative species that you have been talking about here.
Amino acids are notorious for supplying nitrogen to both microbes and plants. And in some experiments, they've done just as well up against urea, for example. Not all the time, but some of the time. So yeah, it's a great nitrogen source. It's a carbon-based nitrogen source, which really puts it in a kind of a league separate from inorganic chemistry. But then to discover all the things that the amino acids do, and glutamate makes more amino acids. Amino acids end up as complete protein if everything's going right. And then you got a healthy plant.
In our industry right now, amino acid is a hot topic, and I honestly don't believe, and I'll say this on a very personal level, I'm not sure I understood completely what an amino acid, a lot of folks are talking about, we've got amino acids here, we've got amino acids there, I spray amino acids. I'm not sure everybody that's listening or everybody that's in our industry really understands what the value is, and forgetting the science, forgetting the detail of the chemistry, but just from a practical standpoint, one of the things that you've taught us is that the value of the amino acids are certainly helping us primarily with this reducing the oxidation process, and so which is huge, reducing stress. My understanding is that they don't get taken up easily. And what you had taught us as well is that there is a big difference between amino acids coming from natural sources versus some that are synthesized, which I'm not sure I fully understand, and I'd love you to explain the difference between natural and synthesized. But let's start by just simply a very simple, common sense 101 explanation of why would we care about having amino acids in our products? What are they doing for the superintendent, the golf turf manager? Give us a quick, 101 shot of amino acids.
They're supplying nutrients, and they're also supplying, they're supporting enzymatic activity because of their complexity. And they're supporting so many biological systems that they provide more diversity for the plant to operate. And when we look at naturally occurring amino acids, these amino acids in your products are derived from a hydrolysate or hydrolyzed fish meal. And they're more stable, by the way, than most amino acids are. But when you bring amino acids into they're in soil, they're generated by everything. You know, there's plant roots release amino acids. Bacteria and fungi release amino acids because they know they're feeding the system all around them. And when we look at, well, I'm a product developer, so when I look at a product, I'm thinking, I got to have more than just proline. I got to have more than just glycine. I got to have all amino acids that are found in plant systems.
Diversity.
We need that diversity.
Because diversity yields diversity, I think is kind of.
It does.
Because certain biology are going to use more of a certain amino acid than others. So the more that you can have, then you're encouraging this whole spectrum of different biology, different bacteria. I also remember it came up in Jerry's book when talking about the soil food web and how kind of each step in that soil food web increased the carbon to nitrogen ratio, but it starts very small with bacteria being more nitrogen than anything else, and that nitrogen really came from the amino acids. That the bacteria are really like a 5-to-1 carbon to nitrogen, whereas it works its way up the soil food web to be more carbon, more like the earthworms, more like a 30-to-1 carbon to nitrogen ratio. But the start of all that nitrogen is very down elemental, down to the pieces of protein, the amino acids.
Yeah, where does that nitrogen come from that plants utilize long before fertilizers were invented?
Right.
And yeah, it comes from naturally occurring nitrogen materials. This is one of many. This is just one of many, many, many. We're kind of focusing on one right now, but it fits the principles of biological agriculture, biological growing, and it fits the principles of diversity. It fits the principles of bioavailability, which we could get into. It fits the principles of diversity. So take away any of those and you have a weakened system. Put them all in there. And okay, you mentioned Jerry Bernetti. Okay, when I decided to take on your project, you know, as a consultant and look at your formulations, it was obvious to me that Jerry Bernetti took this shotgun approach
Diversity.
to product development. It was like, and he used to use the word you know what, something will stick. And it's so true. You throw enough on the wall in a barnyard, something will stick, right? And his shotgun approach to biological growth and biodiversity and biologically dependent rather than chemical
bioavailability.
Agriculture. What was that?
And bioavailability.
Bioavailability is such a huge leap in a paradigm. It's a paradigm leap to what we were all told.
Of course, he didn't explain to us how difficult it was going to keep this shotgun approach together in one jug, and that's been the challenge that we've had as a business to be able to keep this diversity. I mean, we look at any one of our products, there's 30-some raw materials in there, where a lot of folks out there might have one or two, but you know, you and Jerry together really were able to figure out how to keep all this stuff in a jug and
we did,
but being a mess. It wasn't easy, was it?
I remember the story about him shipping out I don't know how many pallets to California.
Yeah.
And what we're doing here is developing a living product. These products are alive. They're not dead chemicals. And those bottles were blown up when they got in a hot warehouse.
Well, we've seen that. We've seen bottles that have elephant turds in them, and we've seen bottles that could become cement. But, you know, finally, after years of getting this really down, understanding and maintaining this incredible level of diversity has really helped, you know, our clients to be able to get so much in so little application to get this going. And there's
difficult.
chemistry behind it.
It's difficult. It's more than chemistry. You know, it's so difficult to develop a product that's natural and very much like a soil system and unlike a chemical system that they're usually unstable. You know, the biggest challenge with these products in the beginning was how do we stabilize them without using poisons, you know, without using something that's deleterious to the environment. How do we,
Lawrence,
Yeah.
We were using this term, and I guess this is a Jerry term as well, but it's a great term. You know, we were using this yesterday when we were chatting, biogeochemistry.
Biogeochemistry.
You know, I
Right.
mean, talking about bringing in biology, bringing in minerals. I mean, one of the things that Jerry was so adamant about, and that I think we've really done an extremely strong job in helping our clients be successful, is making sure that we're constantly remineralizing the soil profile, because every time a plant reaches into the soil, it's pulling out some mineral. And when we put in a product that has 60 plus basic elements, every time it goes out, it's remineralizing that root zone with a biological twist. So we've created a biogeochemical reaction in the soil, which, and you can correct me if I'm wrong, is leading to bioavailability, which means the nutrient load becomes so much more available to the plant because we've brought together carbon and mineral and the microbial population. So when you apply a material that is as dense as this, you're going to get a reactivity, a bioavailability. You're going to mobilize the nutrients so much more efficiently. Is that fair?
Very. Yeah. The reason why I'm putting this slide up on the screen of the periodic table all over again for you to see is that if we try to analyze for all of these elements in a soil or in a product, we need to use analytical methods that were developed by geologists, because our agricultural analytical methods overlook and cannot extract almost all these that are on here, with the exception of the majors. In other words, they're in percentages, they're so highly concentrated. Your nitrogen, your carbon, you know, magnesium, calcium, potassium, that sort of thing. But the trace and ultratrace elements need to be analyzed by geochemical analysis, which is what I use when I'm trying to figure out what's in something. What's in the soil? What's in the plant tissue? What's in a product? I use geochemical analysis because it gets it. It gets it all.
Let me go back to the amino acid real quick. And I know this is a controversy that you and I, or you and we, have always kind of struggled with. Amino acids are good chelators, so we know they can stabilize minerals in the root zone. But can an amino acid be taken up in the plant? I mean, a lot of folks are trying to tell us that, oh, we're going to spray this, it's going to all be taken up foliarly. How true is that? I mean, I'm sure there are some that will be taken up, but I'm also sure that there's a lot that will not be taken up. Or you can correct me if I'm wrong on any of these thoughts.
Yeah, there's protein and enzymatic transport systems that can bring amino acids into the plant foliar application, but not as great as the amount of, or what I say, more effective. The more effective way of bringing in amino acids into a plant is through the root system. And Jack, one of the major ways that plants bring in microbes and amino acids into the root system is rhizophagy.
Right.
Which is just relatively recent.
Yeah. Talk about that, Jack. I mean, I know this has been your baby, and it's so fascinating. I actually had a chance to chat with some clients today trying to explain that and use our graphic, but talk about rhizophagy.
So, you know, it tied in with what we were looking at before in the types of reactive oxygen species. One of them was this superoxide, and in the description of this research that was performed, and what they discovered was that the plant first of all colonizes and essentially farms microbial systems to help deliver nutrient to that plant. That's something that we talk about all the time, and that has been discussed all the time. What rhizophagy more is how does that happen? How does the plant how do microbes assist in the plant uptaking nutrient? And what is seen is that the plant is actually the plant root is actually engulfing and encompassing biology, microbiology, bacteria, fungi, and within that plant cell, then within the root, that superoxide, which is one of the reactive oxygen species, is used to extract material, let's say from the microbiology, from that bacteria,
Nutrients, minerals.
nutrients, minerals, but maybe more amino acids, like more bigger
Yeah.
pieces of the nutrients, minerals. So, and then what's so cool is that it doesn't exactly kill all of that biology. The plant
That's
doesn't kill
amazing.
all of that biology when it happens. It's like, yeah, it's so cool. It's so much the way nature works, right? Nature works to proliferate, to keep it going. So those microbes then exit the plant, and in exiting the plant, they spur new root development. All this happens at
Root hairs.
yeah, all this, what's very important is that this happens in new roots. It happens in new development, new soft tissue, where this engulfing and extracting and then release of biology back into the rhizosphere can actually happen. And we see this in our side so much, you know, talking with clients and superintendents, field managers. They're looking for white roots, right? That's what when they feel comfortable is when they stick the knife in the ground and see, okay, I've got a lot of white roots here. I got a lot of activity.
Rhizophage is working.
Rhizophage is working. So anyway, this research really kind of showed how this is happening. But I was reminded of it when you were talking about the ROS, in that it's a balance, right? In order to reduce ROS, there has to be ROS to trigger that reduction. In order to benefit from from reducing stress, there has to be stress. But the plant knows how to use that superoxide that's developing. Well, it uses it by extracting nutrient material, amino acids out of the actual biology that it's taken in.
You know, we have run up against our hour, but let me just finish up a little bit. You know, one of the part of the rhizophagy is the plant spitting out organic acids, trying to draw you know, these biological species to the root system. One of the things that can happen very effectively is that we stimulate that process without the plant having to put a lot of energy into spitting out carbonic acids and trying to bring this population around. You know, one of the things that, you know, we broached on but really didn't get into any great detail is this concept of, and Lawrence, you did broach it, but this concept of building products that are diverse. I mean, the diversity that we bring to the table, that we can bring to the table, feeds a huge population of microbial activity, and it feeds them for a very long time. I mean, you and I worked yesterday on going through a lot of the raw materials that we work with, and we kind of rated it as a short chain, medium chain, long chain carbon. The short chain carbons being the sugars and some of our surfactants, you know, the materials like the seawater and the fermentation solids. All of these things are getting quick stimulation. Then you move down into the fish meals, the worm teas, the kelp meals. You've got a different feeding process, and you're feeding not only longer, but probably different species. And then it all gets tied together with that incredible humic acid complex that you built for us. But it's that diversity, and it's diversity in a program that really makes sense. I was working with a client today up in Canada, and he was saying, well, there are really no silver bullets in fertility, are there? And I said, no, there really aren't. But if there were a silver bullet, it would be diversity, because a lot of folks are now talking about, oh, they'll throw a little fertilizer in with some humic acid, and they'll throw maybe a little bit of kelp meal with a fertilizer. But it's this real dynamic process that generates that real active rhizophagy in the cycle. And what you've really taught us is the value, and obviously Jerry has taught us the value of feeding multiple populations, you know. And as we know, I mean, we're scratching the surface on microbial activity. We have no idea how many there really are, but we do know we can feed them pretty aggressively, and we do know if we feed them with a lot of stuff, like you said, I mean, how many raw materials are we dealing with in some of these things that you're working with? How you keep it together in a bottle is beyond me. But diversity is, yeah, well, and we've had our challenges, haven't we? I hate to do this, guys. Yeah, I hate to do this, but I'm gonna pull the plug, because we could go on forever. But Lawrence, I can't thank you enough for all you do for us. Like I said, for those of you who are listening, Jack and I and the rest of our team have the real luxury of going through this level of dissertation every Monday. So if anybody's trying to call us at Monday around 10 o'clock, 11 o'clock, don't bother, because we're talking to Lawrence. And after that, we're probably taking a nap and taking some aspirin, because our head's so full of stuff that we don't really understand. Jack, any other last thoughts to share or to ask of Lawrence before we sign off?
Yeah, I mean, I think we were just one little bit, because you had asked about the amino acids being taken in by the plant, and I think we kind of established that yes, it can happen in the stomata, but it's not as effective as when it happens in the bigger root system.
Right.
And that, when that is taken in, Lawrence, first of all, it is taken in the bigger root system, and what's happening in the next step. I mean, we talked about those amino acids really in the human health. In the human health analogy, it was like ROS is like inflammation, and those amino acids are like antioxidants, right? Like we eat antioxidants, we get antioxidants into our body to reduce inflammation.
Well, not directly.
Okay.
They have multiple functions in a plant, and one of them being nutrients, and a very diverse source of nitrogen and other nutrients, which allows the plant to generate what it needs to do to calm down the inflammation, essentially. And it just provides such a diverse form of nutrients that the plants are able to do more than just one thing. They can do many, many things to combat the ROS and utilize them as nutrients. Increase in chlorophyll, that's a big one right there. Now the plant has the energy to go forward and build its natural defenses.
Make more carbonic acid to feed more microbes in the soil.
It just can do so much with it. It just creates more diversity.
Yeah. Well, and then one other point about the diversity, this line came up in our call on Monday. The nature of what we do is not natural, right?
That was a good one, Jack.
Yeah. Jack was very proud of that. He came up with it. It's good, though. It's very, very, very good.
I wasn't about to claim it.
No, you can. It's yours. I like it. I'm going to steal it from you. You know that.
So, oh, yeah, that's fine. I mean, but that's what we were saying. And that's really, we
true.
talked about that forever, is that the golf course, the sports field, the home lawn, it's not a natural system exactly. It's not, it's not the meadow, it's not the grasslands of the Midwest, in the last millennia, but what we're doing in the biological soil management in these products is that we're trying to bring more nature and more diversity into that system. The nature of managing a lawn is not really natural, but we can bring a lot of those natural processes into our management
by using natural products.
There you go.
Right.
So with that, folks, like I said, we could continue this conversation for hours, and we do often, and it gets, we're never at a loss for new information, and how incredible is it, at our ages, we can continue to learn the process, but we will have you back, I promise you, Mr. Mayhew. But again, thank you, Lawrence Mayhew, and thank you, Jack Higgins. And this is the EarthWorks podcast. If you're not signed up as a subscriber, please do, because we put a lot of stuff out there that can be very entertaining and certainly very informative. So thank you both. We will be back next week with another EarthWorks podcast.
All right.